So we've looked at sine, cosine, tangent, secant, cosecant, cotangent, and now we can look at some identities. You probably have seen, those little cheat sheets with a list of trig identities. We'll go through a couple of them, and then some I'll just list and refer to. You don't spend time memorizing all of these identities. It's more useful understanding how some of the fundamental ones work, and then trusting that the other ones work, and just pulling them from your textbook. Um, you don't use them often enough in a practical engineering sense for you where you wouldn't be able to reference some kind of textbook when you do need to use it. So we'll go through a couple of them and show you some graphs to convince you of why they work. And then some of the more elaborate ones, I'll just show you a list and just talk at a high level. So this set uses the Pythagorean theorem. Remember when early in this series we looked at a squared plus b squared equals c squared, referencing the sides of a right triangle where c is your hypotenuse, and we can build. And this is probably the one I use the most often. So sine squared plus cosine squared of the same angle is equal to 1. This shows up a lot in a variety of derivations. And this allows you to drop terms out. A lot of times sine squared plus cosine squared, then you have something multiplied by this, and then this term will drop out. And so it simplifies things quite a bit. So let's see, right? We define sine theta. So theta here would be b over c. Cosine theta would be a over c. And then there's your Pythagorean theorem. And if I just take the Pythagorean theorem as is and divide by c squared or c, we get a over c squared, which is just cosine theta, plus b over c squared, which is just sine theta squared, is equal to c over c squared, which equals 1. And so very simple derivation shown here. And we can use the Pythagorean theorem, manipulate it a couple different ways, and we'll see 2 other identities come from this. So we got secant. So from, again, looking at theta, we'll get c over a, and where secant is just a reciprocal of cosine. Then we have tangent, which is b over a. And then if I rewrite the Pythagorean theorem as c squared minus b squared over or equals a squared and divide by a squared, I get my c over a quantity squared, that's my secant squared, minus b over a quantity squared, that's my tangent squared term, equals a squared over a squared, which is just 1. So I get my second identity. And then my third identity, I got a definition for cosecant. Remember, that's just 1 over my sine. Cotan, just 1 over my tan. And then we rewrite the Pythagorean theorem as c squared minus a squared equals b squared, and basically do the same thing to get the relationship between cosecant squared minus cotan squared equals 1. Right? So to be honest, I don't really use these 2 forms. I usually use sine squared plus cosine squared equals 1. That's the one that shows up over and over. But just know that these just come from the Pythagorean theorem and the definitions of the trig functions. I would memorize this one because this gets used enough that it would be useful to have. And then these other 2 I would just have on some kind of sheet, maybe at the back of your calculator. Let's take a look at some other identities. So when we look at our 6 trig functions, we can distinguish them either as an even trig function, which means that if I put in a negative theta, that I get out the same as if I put a positive theta term. Or I would have an odd trig function, which says that if I plug in negative theta, I would get the negative of the function with the theta term. And you can really easily see this from the graphical form, and we'll show you that here. And I'll show how actually for each of these 6 trig functions, how it shows up with a negative theta term. And it's also very useful to look at the unit circle. So it's important to remember what a negative theta or a positive theta represents. So the positive x-axis represents our 0 theta, or 0 degrees or 0 radians. A positive theta starts from the positive x-axis and goes counterclockwise into the first quadrant up here. A negative theta starts here and goes down into the fourth quadrant, down here towards the negative y-axis. So what we're looking at is whether, like, do we, for the trig function that we're specifically looking at, do we have x values? Do we have y values? If you just have x values in your function, then whether you go in the first quadrant or fourth quadrant, your function doesn't know the difference, right? So theta, positive or negative, looks the same to it. If you have y terms in it, right? In the first quadrant, it's a positive y. In the fourth quadrant, it's a negative y. So then it would have a difference, and it would be represented by the negative of that function. So we're going to take a look at some graphs of the trig functions and we've seen this over and over in the past few videos, but we'll use it and think the negative theta will be represented as the x-axis. The function itself is obviously the y-axis, and it'll be pretty apparent which one of these, whether it's even or odd, just graphically look at it. So let's take a look at a few of these. All right, so here we have cosine and secant, right? So secant is just 1 over cosine, right? So if we're looking at from the unit circle perspective, this is basically for cosine x over 1, and for secant 1 over x. And I show the graphs of both down here. And there is no y term, so I would expect that a theta, positive or negative, would look no different. And you can kind of see that here, right? The negative theta is on the left side of this graph. The positive theta is on the right side of this graph. If I swapped out any of those terms and they're the same, it's basically saying if I fold along the y-axis, right? If I fold on top of it, the graph, it will fall on top of itself. Let's take a look at some of our other trig functions. Here we have sine and cosecant. So again, if we're looking at it from the perspective of the unit circle, the hypotenuse is 1, the opposite side is y, right? The y term. So I put in red here to emphasize the y term is going to be affected by a positive or negative theta term, right? So this will be considered an odd trig function. So you can look at this graph here. If you fold along the y-axis, you do not fall on top. You would fall on top of the negative form, right? So like, for example, on the sine curve, if you fold it across, you'll be positive when it's showing up as negative over here. You can see it for the cosecant as well. And so I would consider this odd trig function. For the tangent and cotan, as shown here, it's a little bit messier, but you can see the same thing as well, right? If I fold across that y-axis, I'm not going to fall on top. I would have to do a negative sign to flip everything before it laid directly on top. So we can take a look at each of these segments a little bit closer and actually show you graphs of the negative theta as well as a negative of the function to see which ones overlap each other. So we talked about sine and cosecant as odd trig functions. So when I plug in a negative theta, this would match a negative function with a positive theta term. So what am I saying? I'm saying sine theta is shown in red here. The negative sine theta is shown in blue, which is also the same thing as if I wrote sine negative theta. And the reason why that's true is because there's a y term here. So it's positive y over 1 when it's sine positive theta. When it's sine negative theta, this is a negative y over 1 because it's in the fourth quadrant, or a negative sine theta, which would be the same thing, right? And similarly, for cosecant, you get the same behavior because it's just 1 over it, right? So in red, here we have cosecant, and then in blue we have both negative cosecant and cosecant of negative theta, right? So the trig identities would be recognizing that sine and cosecant are odd trig functions. Now you can simplify things, just remember what sine is, and intuitively you would know that cosecant is because it's the reciprocal. Okay, so let's take a look at cosine and secant. So as we said earlier, cosine and secant do not have y values in here. So they're not going to know the difference between positive or negative theta. So because of that, it's an even trig function. And again, right, that's folding across that y-axis. So if I look at cosine theta, this will now be equal to cosine negative theta. And that's shown in the red graph here. If I just said negative cosine theta, I would take my red graph, right, that cosine theta term, and I would fold it across the x-axis, and that's what's shown in blue, right? That's negative cosine theta, which is represented as a negative x over 1, right? So because that is not equal to cosine negative theta, then that means we have an even trig function. Similarly, we have secant theta equal to secant negative theta, because it's just the reciprocal of cosine, and negative secant theta is shown as not equal to secant negative theta. So it's definitely not an odd trig function. This is also an even trig function. And finally, we have tangent and cotan, right? So both have the y value. So it will be affected just like sine and cosecant were. And again, this would be an odd trig function, and we can see that because if you fold along the y-axis, you need to do the negative sign to mirror it. So we show the graph of tangent here in red, right? Negative tangent is flipping it across the x-axis. That's what's shown in blue. Or you can think about it as tan of negative theta will be folding it across the y-axis, and that's also shown in blue. So it's kind of like a diagonal fold for it to match. That's why we have this as an odd trig function. And cotan shown in red. And this is the same idea, right? Because this is just 1 over the tan term. And negative cotan theta is you take that red graph, fold it across, fold it across the x-axis, and cotan negative theta is folding across the y-axis. And you see, so the identities are whether it's an odd or even trig function, and that can be useful. So this is one that I would memorize for sine, cosine, and tangent, and then I would rely on my understanding of the relationship between those 3 main trig functions and secant, cosecant, and cotan for you to utilize this one. So this one's worth memorizing because it shows up quite a bit. And we've talked about phase shifts quite a bit, especially for sine and cosine. And these are worth remembering, at least understanding the concept. Now, the nice thing is you can easily graph the fundamentals like we show here, right? So the graphs itself show no phase shift. And the identities out here, we can talk through of how a delay or push forward would reflect that phase shift. These are worth understanding how to recognize it, because phase shifts show up a lot in engineering applications, either forced or when you're trying to control a phase shift. So here in red, we have sine theta, and in green, cosine theta. So this first identity, sine theta is equal to cosine theta minus pi over 2, says that if I delay or do a phase shift for cosine by pi over 2, I would match sine theta. So in green, a phase shift is basically saying I'm delaying where this peak starts by pi over 2. So delaying it is shifting it to the right. If you shift it to the right, then the reverse, right, cosine theta, if I want sine theta to match it, I need to pull back or start earlier, right? That's what the positive sign is saying for sine by pi over 2. So it's like taking this red peak and starting it earlier, because a negative pi over 2 for theta in this function for the sine term is not here, it's down here. So it's pulling it back, right? So similarly, we see that same behavior in cosecant and secant, right? Cosecant is 1 over sine, and secant is 1 over cosine. So it makes sense the phase shift behavior would be the same here. For tangent and cotan, you have to have a negative in front of theta. Sometimes they'll write this as pi over 2 minus theta instead. So first I'll explain the negative, the reason why we need a negative form here. So for sine and cosine, we can shift the graph left and right, and then it'll lay over. Same thing for secant and cosecant. For tangent and cotan, we can't. You can see the shape of the red and green graphs are not the same. No matter how much I shift it left or right, it will not match. So the negative theta will flip the graph, right? So like we talked about the odd and even functions, right? So that's part of the importance of it. It will flip the graph, but even if I just flip the graph, I still need a pi over 2 phase shift. Now I have plus or minus pi over 2 because it doesn't matter if I shift, right? Let's say I mirrored flip the red graph, right? The tangent graph. If I shift it back pi over 2, or if I shift it forward pi over 2, because it's in the middle, the period is shifted, it is split directly in half, it will work either way. For sine and cosine, your period is 2 pi, and you're not shifted by pi, so it doesn't work the same way there. You could think about it as minus pi over 2 or minus or plus 3 pi over 2. You could do it that way, but usually we just use pi over 2 minus plus or minus as the phase shift to keep things simpler, right? So the phase shift piece is important. I would memorize it for sine and cosine. For secant and cosecant, that's kind of intuitive because of sine and cosine behavior. For tangent cotan, I don't generally memorize it myself. A graph would help you already determine that, but knowing that there is a phase shift is important. And then when you do want to do any kind of controls, you do usually have time, so you can look it up and look at the graph. I mean, I would refer back to something like this to help jog your memory of how you would control it. And there are other identities, right? These are the common ones that I will see on a trig cheat sheet with a list. But these, you know, this is way too much to memorize. There's no real point in memorizing. What I would know is that if I see a 2 theta in my derivation or in my calculation, I know that I could go to my table and look these up. I would memorize that 2 theta shows up in the table. I would memorize that if I have a plus or minus of 2 angles, right, within my trig function, I could look up and simplify that. I could look up and simplify if I have 2 trig functions that are added together or multiplied together. So recognizing that there are simplifications that I can refer to, that piece of it is important to know. But to memorize all this is, in my opinion, a waste of time, because there's just too much that you can memorize incorrectly, and there's other things that you're going to have to remember. So I would just, if you Google trig identities, you'll see a ton of different sheets with all of the ones that I just discussed. I would memorize the phase shift, or memorize or at least understand the odd or even functions or how to distinguish them. And I would memorize sine squared plus cosine squared equals 1. Beyond that, you'll see that you can manipulate these different trig identities to make it work for you, or you just get the computer to solve it for you. So don't waste your time memorizing all these different components. Make sure you understand the behavior of sine, cosine, and tangent and how to manipulate them. That would be much more useful. So that already encapsulates a lot of the pieces of trig that you get used over and over in engineering and physics problems. And we're gonna, in the next set of videos, look at some actual applications, and you'll see how what we talked about from a mathematical perspective is then applied to a physical perspective. And that's the power that we can actually use these trig identities and trig functions.